El tiempo. This is a clock, good, not super good clock. See another one? If I raise this one, meter, I wait a little bit, 1, 2, 3, 4, 5, and then I bring them together. If these were very good clocks, this is not very good clock, this is a commercial clock, but if this was a very, very good clock, this one would be late with respect to this one. The one up would have measured more time than the one down. So this is not a theory, some complicated hypothesis. It's a fact that today can be measured easily in many physics laboratory. They're good clocks, very good clocks, better than these ones. And in fact, it can be measured at 30, 40 centimeters of difference. Time passes more up than down. Time flows faster up than down. Which means, for instance, that if you have two twin brothers who are born here in Antofagasta, and one of the two goes up in the mountain in San Pedro, and they spend their life, one down and one up in the mountains. When they meet again, after many years, the one up is a little bit older. Like that. Okay? Now, of course, we don't see that usually because the effect is very small, and because we don't have a good sense of precise time. We don't perceive small differences of time. It will not be so so enormously older, the one up in the mountain. It will be a little bit older. But if we were on a planet bigger, Jupiter, who is more heavy, or near a sun, or near a black hole, the effect would be very strong. So if I could take a spaceship and go very, very close to a black hole with engines to avoid being eaten by the black hole, keeping outside but close, and wait 10 minutes, and then move out and come back on Earth. On Earth, there are maybe 2,000 years that have passed. So time goes slower when you go down near a planet, near a star, near a black hole, slower and slower, and faster outside, which means it's easy to go to the future. It's just an issue of money. If we could make a starship, go near a black hole, come back, we could go as much as we want into the future. Again, this is a fact we don't perceive, and a fact that tells us that time works differently than what we usually think. There is no big clock outside the universe that says 1 hour, 2 hours, 3 hours. Time passes at different speed in different positions. Now, a beautiful thing is that all this was understood before measuring it. Today is easy. You just take good clocks in a physics laboratory, put one up, one down, and you check this. It's a fact. The satellites, the clocks for the GPS, and engineers know that the clocks on the satellites go faster. Time passes faster on the satellite than here. But this was understood before measuring it by this guy, who's everybody knows is Albert Einstein, 100 years ago. And how did he do this? How could he understand that before measuring it? Well, by physics, theoretical physics. How? By taking what was known at the time about the world, Newton theory, Maxwell theory, and finding how they could, taken together, tell us more about the world. Find contradiction in what was a world picture of his time, find what was not working well, and on the basis of that, asking how can I bring them together, and realizing that to do so, he had to change something in the way we think about it. And this has happened over and over again in physics. It's still happening now, and I'll tell you in a little time how me and my colleagues are still trying to do the same thing. On the basis of what we know about the world, learn more, look for the things which are not clear, and on this basis try to guess how the world works. And to do that requires to changing our image of the world. Let me tell you one consequence of the fact that time goes faster here. Suppose I take an object, this object, I throw it up, it comes down, whoops, and I'm going to break it. It comes down, I'm going to do it again, 1, 2. Why does it do so? Why it comes down? Let's see, I throw it up, suppose this is up, down, this is time. Time is this way. So I throw it up, time passes and it comes down, okay? So it does this line. Why doesn't it go straight? Things go straight. Well, you have learned at school, I've learned at school, that is because of the force of gravity pull. But this was the old understanding. Now we understand it better, and the reason things come down is because time goes faster here than here. Let me explain you. In space-time, so this is space, up, down, and this is time, okay? This line that this draws, it's actually straight. What does it mean? Well, suppose you have to take a plane and fly from Santiago to Cape Town. It's upside down because we're in the south hemisphere. I think that's the way you people in the south hemisphere so represent the world. There's no reason you're down, right? You could put yourself up. So if you fly from Cape Town to Santiago, and you would say, well, I should go straight. But planes don't go straight. Why planes don't go straight? Well, because up south, the east and the west are closer than down. So moving east-west, it's convenient to go up a little bit and then down. Up, south, and then down. Why? Well, because the world is curved. The planet is curved. In fact, if you take the globe and look at it, it's obvious that that one is the shortest line, right? So that's a straight line in a curved space. And exactly the same manner, this one is a straight line in a curved space-time. It's exactly the same mathematics, exactly the same. You see, physics redraws the world, changes the world, and our usual picture of the world, that's our usual picture of the world. There are things in space, there's up, there's down, the sky, the earth, and time goes on. This is our immediate vision of the world, but that's not right. It doesn't. The world is not like that. Time, as I told you, is it's a little bit different. Time's different up and. What about up and down? Arriba, abajo. I just learned. Well, we all know that that's also is wrong, right? Up, down, sky, earth? No, it's a little bit complicated. In Antofagasta, up is not the same direction that up in my own country, in Italy, right? This is up in Antofagasta, that's up in Italy, okay? And in fact, if you go out of the Earth, there is no up and down whatsoever, right? This is some astronauts in the space. If you go very far away from the Earth, there's no meaning of up and down. Up and down are just not good things to think about the world. The universe does not have the up in the universe and the down in the universe. So up and down, they're not false, they're not illusions, but are notions which are good here, in this our little corner of the universe. In our little, in Antofagasta, a little bit more somewhere, but not outside in the big universe. Up and down are local things, they're not characteristic of the universe. And the time that passes all together it's not a characteristic of the universe. The universe is different. Of course, now we know very well that the Earth is round and it operates at different directions. Let me talk about space, because this is a spatial. This is the other thing that Mr. Einstein changed a lot. And recently, there have been beautiful confirmation of Einstein's ideas. So Einstein understood that not only space-time stretches, time stretches there with respect to there, but space itself, let's forget time, space itself can stretch, can bend, can wave, can move, and he wrote some equations that describe how this happens. So this is an intuitive picture. Imagine some planets or some balls that move, and space can do waves, can bend, and in fact it can bend so much, space and space-time can bend so much, can stretch so much that the universe together can grow. We know the universe is growing. We know it expanded from a very hot condensed point, which is a Big Bang down there. We know very little about the Big Bang. Expanded. But it's not the matter that expanded. Space itself is growing, and somewhere space can bend so much to make a black hole. Black hole, it's a place where space falls down, and here, I told you, time slows. Here, on the surface of this black hole, time stops. If you put a clock there, it just doesn't move anymore. A plant there stays there, doesn't move. And I like black hole particularly. Everybody likes black hole, but I'm particularly attached to black holes because when I went to school, not so long ago, I was told that black holes do not exist. It was written in my books, books written by a Nobel Prize in physics, that what is a black hole? Black hole is a solution of the equations written by Einstein. So it's something predicted by the theory by Einstein. But nobody believed they actually existed in the universe. So I grew up thinking, all right, those nice, beautiful things, but they don't exist. And in fact, they exist, and now we see many, astronomers see many. There's a black hole there. We see the effect of black holes. We see many things about black holes. So it helped me to understand that what is told at school is not necessarily true. Sometimes it's false. Books may be false. And that's the core of science. What is science? Science is the capacity of thinking different than before. We build on our past knowledge. Of course, Einstein understood what he understood on the basis of previous theories, but we understand that we may learn. We can learn more than what was known in the past, which means that what was known in the past may be wrong. Science is about doubting, having doubts, questioning the past knowledge. Science is the attitude that says, good, we know all these things, but maybe something is wrong here. So it's the attitude of not trusting previous knowledge, not trusting tradition, not trusting what our fathers and grandfathers knew. They knew stuff we may know better, okay? On the basis of what they knew, but learning more and more. So let's get back to black holes. Black holes, now we know there are many in the sky, and sometimes there are two black holes that turn one around the other one, that spiral one against the other one, and when they spiral, they shake space around, and they make waves. The space waves around, like if you have a piece of fabric, you move it, and then you make waves on the fabric. The same space itself waves, and this is a computation that was done recently from the Einstein equations that shows how the waves are formed, of course it's three-dimensional, not two-dimensional, how the waves are formed around two spiraling black holes. in the center, there are two black holes. Now we're going to see them a little bit. And they create, you see the two black holes there, that go one around the other, and they create these waves, three-dimensional, all around. And in fact, these waves have been detected 1 or 2 months ago, and it was big news in the all around the world, with a big antenna, which is the LIGO antenna in North America, in the United States, which is an antenna to detect this wave. These were two black holes falling into one another, and the moment in which they fall into one another, the waves are stronger and stronger. It happened obviously many times in the universe, because if we have seen one, it means there are many. And this one we have seen happened 1 billion years ago, very far. So two black holes spiral one into one another, and make this boom, this whoop, this big explosion of waves. And the wave traveled for 1 billion years, and we could detect them with this machine here, with LIGO. This is the actual signal of the detection. So space is different than what we think. Time is different. What we think up and down different. What we think. What about things? Process. What about things? A piece of plastic, or the walls, the air, the mountains, what we see around us. This is take any landscape, okay? What we know, and of course, if you think for a moment, it's sort of obvious. What is there? Well, a mountain, some animals, a lake. That's it. That's it. Now, if you zoom in, maybe there are all sorts of vegetables. Maybe there's a flower. Maybe on the flower there is a bag. Inside the bag there's complicated organic structure. You go in, there are atoms, and the atoms have a complicated structure. In this piece of plastic, inside, it's an incredibly complicated action of quanta moving, appearing, disappearing. There's a lot of empty space, a lot of... this is, in fact, a piece of plastic. In fact, it's not a thing. It's a process. It's like a wave. Like if you look at the ocean, you see these big waves. The wave move, but the wave is not a thing. Water just goes up and down. The wave passes. So you see the wave here, the wave here, the wave. But in which sense this wave is the same as that? Is the same as the same wave before? Well, it's just a continuing process. And this is the same. It's a process happening. You are the same. You're a process, right? Atoms come in, go out, and things happen. And we are happenings. We're not things. There's no an entity which is our soul. It's just the happening of everything that happens in our brain, in our memories. We have memories of the past. That's what connects us with the past. So the world is complicated, and matter itself, it's a very complicated thing which happens. And we have a theory, which is quantum mechanics, that describes very well the minute structure of matter, and how it's probabilistic, it's continuously fluctuating, and is discrete. There's nothing continuous. They're just particles, blip, 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 discretely happening. This is the world that we know, but in fact there's more, because the two big discoveries which I just mentioned, Einstein discovery that space is curved, which is general relativity. This afternoon there will be just a nice talk by Andres Gomberg about Einstein in the afternoon, all his ideas, which I recommend. And quantum mechanics, the theory that tell us that that matter is made by fluctuating grains. These two theories don't talk to one another well. So we're exactly in a situation like Einstein found himself, with different theories, different pieces of knowledge of the world, not combining well. And we might hope to understand better about the world by combining them. And the theory that tries to combine that, and which I and many colleagues work, is called quantum gravity, gravidad quantica, and is the attempt to go ahead, to understand more about the world by bringing together everything we have learned so far. And what does it tell us? So it's very easy. Let me just bring you into quantum gravity. Einstein understands that space-time bends their equations, so it's a field. Physicists call field something that can move like the electric field or the magnetic field with equations. And quantum mechanics tell us that every field is made by grains. The electric field with the light is made by grains, which are the photons. So if you bring them together, these two discoveries, what they imply is that physical space not only bend, like Einstein says, not only time is stretched here with respect to here, but space, or better space-time, it has a granular structure, a fluctuating granular structure. So if we look into in the small, you just zoom in a piece of space, smaller and smaller and smaller. Down there should be some quanta jumping all around that make up space. And the theory that describes that is a theory on which I'm working, describe a space which has like many intertwined loops, they're called lazos, and it's called loop quantum gravity, gravidad quantica a lazos. These are the main equations of the theory. I'm not going to explain you the details of these equations, but I wanted to show them, to show it's nothing magic, it's just a simple set of equations. But these equations describe the world, and if they're right, they describe how the world actually is at a very, very small scale and allows us to understand things. So what do they tell us, this equation? They tell us that space is made by grains of space, quanta of space, and these quanta are connected in a sort of network, una red, and for technical reason this is called a spin network, una red de spin, because it's like this spin is like turning, something turning, but this is just a technical thing. And this net changes, keep changing, locally here and there, and this change is like the passing time everywhere, and by changing, a net changes its structure and makes a structure which is called a spin foam, a spuma de spin, because in the small space-time is like a foam, bubble foam. So the equation tell me how this quanta of space keep changing into one another, and that's an intuitive picture of the minute structure of space-time, how it keep transforming into one another. And what do we do with this theory? All right, so imagine that space-time is like that. Well, we can do what we were not able to do with the previous knowledge and tentatively solve, we have to see if it is right or not, tentatively solve the problems, the things which we do not understand. For instance, we did not understand what happened here. At the Big Bang, the universe expanded, but expanded from what? And if we apply the theory there, we can see that when the universe was very small, this quanta of space stopped. If you go back in time, stop the compression, and there could be a bounce, un rebonde. So the universe may have done that. A previous universe that compressed, becomes very, very small, arrives in a region where space and time are completely discrete and fuzzy, as a cloud of quantum probabilistic atoms of space and time, not usual space and time, and then re-expand. That's our universe. So instead of a big bang, a big bounce, un rebote. The other thing we can do with this theory, which I am working on right now, so I want to tell you what is exciting me right now in science, is to answer the question, what happens inside the black hole? We see these black holes, okay, we see matter falling in, we see things spiraling and falling into black holes. Where does it go? It falls inside, and then what? Well, it's not clear. Nobody really knows, but we have this theory, so we can try to see what happened, because we have the quantum structure of space-time described by our theory. And what the theory tells us is similar to the universe. So imagine a star that collapses, falls into a black hole, goes inside, it gets to a quantum region, and then what? And then it bounces back, reopens, violating the classical Einstein equations. Violating Einstein equations because of quantum mechanics. Boom, boom, explodes. So imagine a black hole, boom, and reopening. Well, that should be wrong, because we see black holes staying there. They don't jump up. But remember that time passes at different speed. So, if you are inside a collapsing star, you fall in, there is a bounce, comes out, 1 millisecond. But if you're outside, time goes much slower or faster. So there's more time passing. And if you do the calculation, a millisecond inside could be 10 billion years. 10 millones de años outside. So a black hole could be just a shortcut to the future. Something doing boom, boom, but from the outside you see it's slow motion. Black hole, black hole, and then billion years later, boom, coming out. And if this is correct, we might see it. Because if in the early universe there was a black hole forming, imagine the early universe, everything was very hot and agitated, right? So there could be some, in the agitation, some black hole forming. If there was black hole forming there, they're called primordial black holes. Astronomers think that they might exist, we are not sure. Then the matter here collapses and immediately bounces, but immediately for somebody inside. Outside, 10 billion years may have passed before it comes out. And when it comes out, a signal may reach us, and we have big telescope, and in particular radio telescope, who could see that. And there are some signals which are observed by radio telescope, and we hope to show that these signals are in fact signals of black holes forming in the early universe, coming out today through this quantum gravitational process. Are we sure? No, not at all. Okay? But we're trying to see, and we are trying to see if we could find make precise predictions on the signal and compare it with what the astronomers see, and so understand something about what happened inside in the small, the center of a black hole, with a quantum theory of gravity, explore the minute structure of a quantum space-time. And telescopes like this one in Chile are exactly what is needed to observe these signals and understand something about the structure of space. So let me try to move toward the end. This is the world I said we see it normally. And time is not really the way not correct the way we think about it. And the up and down is not right, and space is not really space, is something else, and the things are not really the things. So the world is in fact very strange and very different from what it looks like, something completely different from our usual picture, but nevertheless we can understand it. We have some equations, we have some intuition, we can think about that, right? That's the beauty of physics. And what about us in this world? I think that what all this tells us is that we should not think at the world in the old terms of houses, sky, us, our soul, it's much more vast, much more complicated, and we are just one of the many things in the world. I think that the best way of thinking about ourselves is to think that we are just a piece of this enormous complexity, which is more rich, more full of variety than our intuitive notion of it, and allows for galaxies, for black holes, for microstructure, for who knows how many things. Last night here there were pictures about the planets, beautiful picture about the planets, which is a fantastic variety of things in our solar system. Imagine in the entire world, at small scale, at big scale. There are all sorts of things. We are one of these many sort of things. We, our soul, our emotions, our thinking, just a little happening in this big dance, immense dance, which is nature. This is what you see with a telescope if you point a teeny region totally black of the sky. What do you see? You see hundreds of galaxies. So astronomers estimate that there are 100 billion galaxies in the visible sky. It means that sky may be more than the visible one. 100 billions. 100 times millions galaxies. It's an immense number. It's an incredibly large number. And each one of these galaxies, each one of these little teeny dots here, this one, okay? Inside there, it's a galaxy more or less like ours, so like this one. This is Andromeda, it's a galaxy next to us, so it's easy to make a beautiful picture. It's more or less similar to ours. And in each one of these 100 billions of galaxies, something like that, where there are 100 billion stars. So there are 100 billions times 100 billions. It's an incredibly large number. And one of these stars, somewhere it's our sun, with the planets, and now we know, it's a recent few years we have understood that almost all the stars in the galaxies have planets. So there are a fantastic number of planets, and in these, in one of these little planets is us. Okay, so this is a picture I particularly like. This is the Earth. This little dot here is the Earth. In a picture taken by Voyager, which is this starship that is going out from the solar system, it's a picture of ourselves from more far away that we have seen. You see this? It's all there. Antofagasta is in some... and all there. All our dreams, our politics, our pain, our happiness, our empires, our religions, our philosophies, our science, just, all there. Should we believe all this? No. I mean, we should take a we understand something. We understand step by step. What we don't know is still much more than what we know. I think we should be ready to give up our old ideas about space, about time, about things, about soul, about God, about power, about... they're useful. They're useful. We can live, but we should know that they're very approximate. And science gives us a little bit more. Science gives us at least the knowledge, the understanding that this is partial, and offers to us a view of the universe, but certainly the reality that we mostly see about us is much more than it looks to us. Thank you very much.